recording. Okay, so good afternoon, everyone. Good evening. So welcome to the renewed Colloquium series. So we had some time off after the online culture started, and now we are getting back. And today we are especially honored to have Professor Tien Cuong from one of the stars of the math department in National University of Singapore. You probably read the poster for the honors. And it's part of a two-man show. So this morning we witnessed one of Professor Din's students who explained us the basics of complex dynamics, and this is the main event. So Professor Din will tell us about. I have the title here. Sorry, I lost the title.
Okay. So
about the latest news in complex dynamics. So please.
Yeah. Okay. Thank you very much for the invitation. So I'm very happy to be in your department virtually and to know you. So let me share the screen. So I'm talking about the dynamics of foliation. Okay, so so I'm talking about the unique ergodicity for foliation on compact Kaehler surface. So this is my joint work with Nguyen and Sibony. So this morning, I think Lucas already introduced some notation, but so let me introduce some basic notation that I'm going to use in this talk. So let's consider some complex manifold, compact complex manifold for simplicity. So I assume that the dimension here is equal to k larger or equal to 2. So you can take an example as a compactification of CK. So this is a complex positive space. Just take the compactification, the standard one, by putting some hyperplane at infinity. So this is a main example. So a foliation by Riemann surface that we consider here, locally it looks like this picture, this one. So if you use some change of coordinates, so local coordinates, so we have a nice structure like that. So here horizontally you have the unit disk, and transversally you have some, like, let's say some ball for simplicity. So it's the picture is simple like that locally. You can define foliation by locally also using some nowhere vanishing holomorphic vector field. So let me show you the picture. So in the first picture here, you have the local the Riemann picture if with a holomorphic vector field, but locally you can change the coordinates so that the vector field is constant, and then you have this nice picture as before. So here we need to assume that the holomorphic vector field doesn't vanish. But then we can consider a more general case where vector field can have some zeros, And then you have the foliations with singularity. So I'm not going to give you more precise, more formal definition, but it could be something look like picture can look like that. Okay, so in this picture you see that there is some singularity like that. Yeah. But the set of singularity can be bigger. But anyway, here we can accept some singularities, and we can also consider the notion of foliation, of lamination. So by lamination, you don't assume that the family of blue curve here is transversally holomorphic. You don't need this condition, and you can also change the transversal B by some set like a metric space or even a Cantor set and so on. But I'm going to skip this situation for simplicity. So let's consider the case of holomorphic foliation with singularities. So please stop me if you have any question. So now a leaf. So locally, so for example, as before, here you have something look like a holomorphic disk. So now a leaf of F, to get a leaf, you extend this Riemann surface to have a maximum Riemann surface. So on this, in this picture, on this Riemann surface, maximum Riemann surface, will be a leaf of my foliation. So usually is a Riemann surface. It could be complicated. It's not closed in general, and it could be dense in the manifold. But if you are lucky, you can have compact. You can have compact Riemann surface, but it's a very particular case. So now the main problem here is like a dynamical system. We want to understand the leaf. We understand the leaf of this foliation. So I will be more precise later. Okay, so in the same picture, you can try to understand it in the following way. So you consider a transversal. So remember that the dimension of X is equal to K in my talk. So you consider a transversal of dimension K minus 1. So here you can see the picture in the following way. So here we have some intersection with the transversal, between the leaves and the transversal, and then you can follow the flow, the leaf, and go here, for example, and then you have a local holomorphic map from this yellow open set of dimension K minus 1 to the second yellow open set here. And you can have another map going to the next yellow open set. So you have a collection of a local holomorphic map, and you can compose them. Of course, it's very complicated because those maps are local, but it's one way to see the foliation and relate it to the iteration of maps. So let me give you some examples of foliation. So now in the case of CK, as before, I mentioned before, so CK is open set in the positive space PK. So we can compactify CK to get PK. So assume that you have a vector field, which is polynomial vector field, holomorphic polynomial vector field on CK, and you consider the integrand curves defined by this vector field. So here is this picture. I have a vector field like that. So when you integrate it, you have some kind of ODE, and you integrate it, and then you have a foliation. And And in PK, for some topological reason, you always have singularities. So this is, you cannot avoid the singularities. In PK, we always have singularities. So somewhere in the picture, we need to have some singularities. So the generic situation is that the singularity are finite. So we have a finite number of points of where the foliation is singular, but outside those points, the foliation is nice, like before. But here at those points, you might have some picture that I draw before. Yeah, so something like that. It could be a little bit. It could be more complicated. And then we say that the singularity in the generic situation, this generic situation, then the singularity are linearizable. So linearizable means that so here you have you can define locally here. You can define by some local vector field. A vector field. So you have in general you have f or v. F equal to the sum of alpha I z I. So assume that the singularity is 0. So d over dzi, yeah, plus the higher order term. So linearizable means that you can change the coordinate so that you can remove this higher order term. So you have in local coordinate you have this linear vector field. So you can solve explicitly the equation and see how the foliation look like locally at those points. So this is a generic situation. And also the leaf hyperbolic. So the leaf hyperbolic in the sense that every leaf is a quotient of the disk by a group, yeah, in the Riemann uniformization theorem. So you quotient the unit disk by some discrete group of automorphism, then you have a leaf. So you don't have something like a C or C star or elliptic curve or something like that. So in a generic situation, all leaves are hyperbolic. So this is due to the work by Jean-Loulou, Brunella, Grussuk, Disnetos, Suarez, and many people. Okay, so here we want to study directly the leaf because we cannot, in general, we cannot solve the equation explicitly. So this is a bigger family of examples, and as I say here, we always have some singularities. Okay, so here's a second family of examples, which is also interesting. So you consider some compact Riemann surface. So S here is a compact Riemann surface. D mod gamma, where gamma is the pi1 of S. You know? Gamma is pi1 of S. So we have a compact Riemann surface. So you consider some action, the action of gamma on the Riemann sphere, for example, of P1. So so here gamma is a group. You can identify gamma to a group of automorphism of D. So the action on D, you can extend it to the action on P1 on the Riemann sphere, EB1. Or you can consider another action also. You can take this as an example, but you can take another action. Okay, so now you have the action of gamma on D and action of gamma on P1. So you consider the diagonal action on the product. And the product of D and P1 is a complex complex surface. And then you identify the diagonal, the orbit of the diagonal action. So Z A you identify with GZ and GA. So you quotient the space by this action. Then you have a compact complex surface. So basically you have the surface S here, and you have a vibration by P1. This is our quotient. And then you see that here I have a foliation by the blue line here, blue curve here. And then when you take a quotient, you have a foliation on X, on the quotient. And in this case, you don't have singularities. So now you can, in order to study the action of gamma, you can study this foliation. So this is one way to see, to study gamma using the foliation. So this is the second family of foliation. There are other examples, but I will not consider here. Okay, so now I'm going to talk about the Birkhoff theorem for foliation, this geometric version of this Birkhoff theorem. Birkhoff theorem is like the law of large numbers in probability theory. But here I discuss a version for foliation. So I have to introduce some notion first. So first I want to talk about hyperbolic terms. So here I consider a foliation as a dynamic consistent. So I have to talk about the term. So the term is hyperbolic. The term is actually for us is the unit disk D with the Poincaré metric. So the Poincaré metric is basically given by this formula plus some. This metric is invariant by automorphism. So the Poincaré distance between 0 and Z is given by log of 1 plus Z over 1 minus Z. So for example, you take a Z equal to 1, then here you have infinity. Yeah? So the diameter of this space is infinity. So this is the reason that I use this notation. So D infinity is for the Poincaré metric. I use a D infinity for the unit disk. So I'm going to, so this is a picture in dimension 2 on the left side, but I'm going to use the picture in dimension 1 because I don't have enough space to draw a picture in dimension 2 in the next picture. So the picture in dimension 1 look like an interval from -1 to 1. Yeah, as you can see here. Okay, so this for me is that is the D infinity, is a Poincaré disk. The Poincaré radius is infinity. So now the term before R. So I consider the disk dr. Dr is a Poincaré disk of radius R for Poincaré metric. So for Euclidean metric, this the disk D O litten R. So litten R is given by this formula. The relation between big R and litten R is like that. So anyway, when litten R go to 1, big R go to infinity. So in my picture, the disk Poincaré disk dr is the deeper blue set here on the right left side and right side. So I'm going to use a picture in dimension 1. So it's some interval from -R to R in my picture. So this is the term. So I will talk a little bit about this later. So now for dynamic consistent, we have to talk about orbits also. So what is an orbit so we fix a point A. So the orbit of A is just the leaf LA containing this point A. So in the picture, you see that the point A is here, and the leaf, the maximal Riemann surface through the point A is the orbit of A. So now we know we are in the situation where LA is hyperbolic Riemann surface. So you have the universal covering map. So this universal covering maps from the point coordinates d infinity to LA, sending 0 to A. So this map is unique up to a rotation. So up to a rotation, this map is unique. So now the orbit before term R, is just the image of dr. So we have a smaller Riemann surface, which stop here, from here to here, yeah, like that. So this is the term before R. So so you can compare with dynamics of a map. So here is the comparison. So assume that you have a map F from let's say x to x. Then the term is n, yeah. The term is n, and the orbit is of A is A, FA, F of FA, and so on. So this the orbit is just a map from n to x. No? It's a map phi from n to x. So 0 is sent to A, 1 is sent to FA, and so on. So this is the orbit of your dynamical system, and then here is parameterized by some map from the term n to the space. So here also we have exactly the same situation. So my term here is d infinity or dr. If you want to stop before the term r, and then the orbit is the image of this term to the leaf by phi a. So this similarly to the classical dynamical system. Yeah. Okay. So now, if I want to discuss the Birkhoff theorem, I need some measure current. So here's the situation. So we want to have something like invariant measure. In dynamical system, we have invariant measure. So what is the invariant measure in this setting? So the idea is like that. So you have some measure here in the transversal. In each transversal, you have some measure. Yeah? The measure so that, for example, here you have the measure, and then you follow the flow, and then you arrive here in the second yellow set. If you want some invariant measure, then you have to you need to have the same measure here. Okay, so you follow the flow and you get the same measure. Or you follow another direction, you have the same measure on another open set. So assume that you have something like that. We say that we have an invariant measure. So it's invariant by flow. So the flow here is not a global flow, but it's a local flow or semi-local flow, like that. It's not global. So assume that you have something like that, then you have an invariant measure. So it's a good candidate to be invariant measure. But unfortunately, in general, this invariant measure doesn't exist. So there are many people who contributed to this. In particular, there's some general statement in this holomorphic setting by Sibony and Kaufman even in the quite nice situation, you don't have this invariant measure. You cannot have this. If you are lucky, you have this, but in general, you don't have this. So, for example, if you have a compact leaf, then you have a measure like that. For example, you have the transversal like that. So you have to put some Dirac mass here and Dirac mass here. Take some Dirac mass, and you follow the flow, then you get the Dirac mass here. And if you follow another way, you also get the Dirac mass. So if you have a compact curve, then this is okay. If the leaf is not compact, you cannot have this because we want the mass to be finite here. So if the leaf is not compact, then you try to do the same, and you have infinite mass. So we are talking about measure with finite mass.
So the invariant measure is on the bigger space or on the transversal?
So actually, it's a global object. You can define globally, but I try to give you some intuition about this. Okay.
So what do you?
Okay, so we can say the following thing.
Some one transversal, and that's what.
So not one 10%. For every 10%, you can have a finite measure, so that when you follow the flow, you go from one measure to another. But you have this measure for every slice, every 10%, not only one. So for example, you have one more here, so you should have a measure here, so that when you go from here to here, you have the same measure. But this here is easy. You can construct measure here is easy, but when you have a more complicated flow, then it's not clear that such a measure exists globally. Okay. So here in this case of compact leaf, then you can do that. It's more clear that I am go later in this. I give you another definition in the sense of currents, and it's a little bit more clear. But here, roughly, you don't have some object like that. You want some global objects that which invariant by flow, by all local flow. Then it doesn't exist. Okay. So I give you the idea first, and then I go to some more formal definition. Yeah, a little bit more formal. So what you can do here? So when you follow the flow, you allow the measure to change in a harmonic way. So okay, accept this for a moment. So if you assume that you allow the measure to change in a harmonic way, then you have a so-called harmonic measure or ddc-closed current. So ddc is like I over pi dd bar, and this is like Laplacian, yeah, like Laplacian in dimension 1. So ddc-closed is like harmonic measure. So like a delta equal to 0, so it's harmonic object. But okay, so the idea is that you allow the measure to change the harmonic in a harmonic way. Then in this case, the harmonic measure always exists. So this due to Garnett, Condon in the case without singularities, and Fornais, Sibony, and Benson for the case with singularities. So you always have this. So this is a good object for us as a dynamic consistent. So now I tell you a little bit more about this. So here I'm talking only about harmonic measure. So locally, how it look like? So in the local model, in the product of D with B, like before, so transversally, in the transversally, you have a positive measure here. positive measure, and on each leaf, on each blue disk here, you have a harmonic function, which is a non-negative harmonic function, almost everywhere, because here we have a measure. So you can consider almost every blue disk, and you assume that there's some harmonic, non-negative harmonic function. So this is a local model of this object. So you have to glue them together. Yeah, if you want to have a global object, you have to glue them together. So it's not clear that such an object exists globally. But actually, by theorem by Benson, Faulkner, Sibony, this always exists globally. So if I define H, the set of all ddc-closed current of mass 1. So there's no notion of mass. So the mass, if the mass is not 1, you can multiply by a constant. Then, like a measure, you can multiply by constant, then you get current of mass 1. And then in this case, you have a convex, compact, simplex. So it looks like a triangle like that, but the dimension can be infinite. Infinite. So we might have a situation where the dimension is infinite. Let me show you another picture. So it looks like a triangle here. So you have some extremal element, like the vertices of this triangle. It's called ergodic currents, or ergodic measure. Is exactly as in the situation of dynamical system. So you have invariant measure, and the extremal points are ergodic. So if you take another point, for example, here, you can decompose it in terms of ergodic measure in a unique way. So this is the meaning of simplex here. So take any points, so any harmonic measure, you can decompose this in a unique way as combination of ergodic measure. As in the case of dynamical system. Yeah. Okay, so now I can give you a definition which is a little bit more formal about current. So a particular case of current is the case of measure. So here I'm talking about measure of finite mass. The mass is finite. So you can see the measure by duality, by duality. So basically, you take the set of continuous function, so the space of continuous functions, and then you take the dual of this space. So if you have a measure, then measure is M here is an element of this dual. So how to see that? You just take any function phi, and you associate to phi the integral of phi with respect to M. So then you can see that M is in the dual space of the space of continuous function. Okay, so this is the way that we see a measure. So now a current is similar. So we consider a current T is also in the dual of some functional space. So instead of function, you consider form. So differential form, and you take the dual. So instead of measure, instead of function, you consider differential form, and the current belong to this dual space. So let's see.
We grilled Lucas about that.
Yeah. So let's see this our example. So here locally you have a positive measure mu, and you have harmonic function ht. So this is a current. This is current because if you take a smooth form of phi, you can consider this integrand. So you take the product of phi with h, and then you take the integrand on each blue disk, and then you take the integrand with respect to mu. Okay, so this gives you a currents, so a local currents, but you can get the global picture by using a partition of unit. You use a partition of unit, then you have a global currents. Okay, so you put it in the D1 of forms, then you see that clearly. So in particular, if you have a sequence of measure mn, you say mn converge to m if for every phi, function phi, the integrand of phi dmn converge to the integrand of phi dm. So we can do exactly the same for currents. Okay, so you define globally as element of the D1 of forms. Locally, it looks like harmonic function times positive measure as I give you here. So this is exactly the notion of harmonic measure that we consider here. Okay, so let me go to the first main theorem. So now assume that we have a harmonic current T directed by the foliation F. And I assume that it's ergodic for simplicity, but I told you that every current can be decomposed into ergodic ones. But for simplicity, I assume that this current is ergodic. Then I take a generic leaf. So for almost every leaf, LA, so I take LA generic. So I stop before the term R. So here, before the term R, okay? So before the hyperbolic term R. So I have this this piece of Riemann surfaces. So this notation is LAR. So the theorem says that if I normalize this correctly, then the limit is equal to T. This is like an ergodic theorem. So let me show you this. So here a remark. So LAR is a current. How you see that? If you have function phi of so I write here phi of a form of degree 2. So you can consider integrand of phi on this LAR. So this is a linear form. Phi give so you have a linear form. Phi mapped to the integrand of phi on LAR. Yeah. So this is a current. So if you normalize this properly, then the limit exists and equal to T. So basically you have to put some here. You put some weight. You put some weight here, and you still have a current. So this is what I'm saying about the normalization. So you normalize this in a good way, then the limit is equal to T. It's like an ergodic theorem. Okay, it's for almost every leaf. almost every leaf have the same behave in the same way. So let me give you another way to see this theorem. So assume that you slice the space using a transversal of dimension k minus 1. So here you have at the points A1, A2, A3, you consider some Dirac mass. Yes, a Dirac mass. And then you average them. So in the classical ergodic theorem of dynamical system, when you average them, then the limit exists and equal to the measure for almost every point. But here we have to average them in another way. You have to put here some weight. Is the weight that I'm talking about that. This basically you can take lambda I equal to 1 minus. So for example, the point AI is equal to the image of CI, like here. Then lambda I is equal to 1 minus the modulus of CI. And this is the same for every R. So basically, you can see this ergodic theorem almost in the same way as the classical Birkhoff theorem, except that you have to put here some weight, and the weight here comes from the fact that we are using a hyperbolic term. So the hyperbolic metric on D is not doesn't look like the standard one. So there's some weight. Yeah. So this is the reason that we have to put some lambda I here. And then the limit is what we have on the transversal. So the limit exists and equal to h mu. So remember that locally you have this transversally you have a measure mu, and you have a function, harmonic function h, harmonic. Okay, so the limit is equal to h mu on the transversal. So this is another way to see the ergodic theorem by using this slice. Anyway, almost every leaf have the same behavior if you put the correct weight on the leaf. Okay, the proof is quite technical. For many reasons, the topology of LA doesn't depend continuously on A, and if you consider the parameter space of leaves, then it's very complicated and you don't have any topology, and you also have singularities. So the idea is to develop the heat equation, the theory of heat equation, but now we have some weight due to our currents. But the key point is that you have to introduce some good Sobolev space, and then after that we use a technical, classical techniques from pluripotential theory and functional analysis. But after having a good norm and good Sobolev space. Okay, I'm not going to discuss the proof here. So let me go to the main theorem of this talk. So now I'm talking about the unique ergodicity for foliation, but now we are in dimension 2, so k equal to 2 here. The dimension of x is equal to 2. I assume that x is a compact Kaehler surface. So I take P2, for example, it's okay. So I need one more hypothesis. So I assume that the singularity are hyperbolic. This is also a generic case. So remember that the singularity, so for example, if you have singularity at 0 here, then the foliation is given by foliation given by something like alpha 1 z1 d over dz1 plus alpha 2 z2 d over dz2. Okay, so we say that the singularity is hyperbolic if alpha 1 over alpha 2 is not Riemann. So this is a generic condition. So in this case, we know better the situation at the point of singularities. Okay, so so in this case, the main theorem says that you have a unique positive ddc-closed current, unique harmonic currents up to a constant. So if you assume that the mass is equal to 1, then you have only 1. Okay, so I come back to this picture that I show you here. So here we have the set of all ddc-closed current of mass 1 is a simplex, but unique ergodicity means that h is equal to 1 point. So we have just these points. Just something of dimension 0. So it's even simpler than the picture I show here. This is a unique ergodicity. Come back to my slides here. Oh, sorry, I forgot another hypothesis. So I assume that F has no invariant positive closed current. So this is a hypothesis here. So let me also come back to this slide here. So we know that from a theorem by, for example, Nessim, Kaufman, we know that in general, the invariant measure doesn't exist, even in the nice situation. But if we are lucky, then it could exist. For example, if you have a compact leaf, then you have an invariant measure. Okay, so if you are lucky, you can have this situation. But here, in the theorem, I assume that there is no invariant positive closed current. And then in this case, we have the unique ergodicity. So the triangle that I give you is just 1 point. So we have only one current directed by F, which is of mass 1. So now, because you have only one current, then if you take a leaf, any leaf, properly normalizes, it converts to T because you have no choice for the limit. You have only 1 point. You have no choice for the limit, so the limit should be T. This for every leaf, not for almost every leaf, but it's for every. So every leaf has the same behavior in the same way. So this is a unique ergodicity that I want to talk about. So let me discuss the hypothesis, the second hypothesis that I give here. The hypothesis about the non-existence of positive closed current. So we have another theorem actually here. So here we don't assume that there exists or not positive closed current, invariant measure. And then you can classify the situation. So here we have 3 possibilities. In the first possibility, here, you have a finite number of invariant curve. You have a finite number of invariant curve and nothing else. So all currents that you have are there. So you may have more than one compact leaf, but you only have a finite number of compact leaf and nothing more as currents. No other invariant currents or harmonic currents. This is the first situation. The second possibility is that you only have closed current. You only have a closed current. So you may have invariant curve or not, but the currents which are diffuse, those currents which are diffuse, they belong to the same cohomology class. So we have only closed current. They belong to the same cohomology class, and this class is nav, not big, and you have something like c squared equal to 0. And the last situation is the situation which is generic, is given by the last theorem. So in this situation, you have a unique, diffuse non-closed ddc-closed current of mass 1, as in the last theorem. And in this case, the cohomology class is nav and big. In particular, c squared is positive. So looking at the cohomology class of this current, you can see if the current is closed or only harmonic. Okay, so if you remove the hypothesis that I gave before, then you can classify the situation. You only have these three possibilities. So here, for example, if you take a generic polynomial vector field in C2, generic vector field, then the line at infinity is the only invariant closed curve, and you have nothing else. You have in the situation A here. If you have the generic vector field, generic one, so you can also have some situation of some surface which are foliated by a complex curve or by Levi-flat hypersurface. Then you are in the situation B. You have some example like that. And the generic situation is the case C, as I told you. This is a generic situation. You have the unique ergodicity. Okay.
So these assumptions about hyperbolic singularities.
This I need this condition. I cannot remove this.
So are they to check, or how common are they?
So at least if you remove this hypothesis, you have more different situation. You have we don't have the classification, but we have more other situation. Yeah.
But for example, for a polynomial vector field, that's what I can imagine. And then is it? So you need the generic assumption to say these assumptions satisfied, or they are always satisfied? Oh
yeah, if you take a generic polynomial vector field, then it's satisfied. Yeah, this condition is generic. This is a generic case. Yeah.
So, but in theory, you can cook up a vector field that will have something.
Yeah, of course, you can have examples that the vector field doesn't satisfy this condition. Then the situation can be very, very complicated. Yeah. You can have situation where you have infinite leaf passing by this point, and you can have more complicated or tangency or something like that. Yeah.
Okay.
So it's possible, but the theorem doesn't apply in this case. In this case, we don't have the classification. Okay, I answer your question.
Yeah. I was trying to get some feeling.
Yeah. Yeah. So I just want to tell you about the key point in the proof. So the key point in the proof is the intersection theory for currents. So let me give you a very rough idea about this. So assume that you have two subset of some manifold X, and assume that delta is the diagonal of X times X. So now you want to consider the intersection of A and B. How to see the intersection of A and B? You can identify this with the product of A and B intersected with the diagonal. Yeah. So this is trivial. We can see that, but the point is that when you have the diagonal and you have some intersection between A times B with delta, and to see this set, you can do the following. You can dilate the coordinate in the normal direction. You can consider some dilation. This doesn't change the intersection. Yeah. But however, you can see the intersection better and better. Okay. So this is the way that you see the intersection of A and B with delta. So now we can try to do the same. Actually, we do that the same, but not for set, but for currents. So we have two currents, T and S. We take some kind of product. It's easy to show that doesn't exist. It's a D1 to the Weierstrass approximation theorem. But anyway, you can define the something like that. And we even don't know if the intersection is meaningful. But you can still do the same. So you dilate the coordinate and you try to see what you can see at the end, at the limit. And then you can see, for example, some cohomology class. You can see, sometimes you can see better, sometimes you can see the real intersection. But this is a theory that we developed it, Sibony and myself. So this is an analytic version of the Fulton intersection theory. So for example, you take two algebraic varieties. So you want to consider the intersection of algebraic varieties, so you can do the same, for example. But in general, when you take the intersection of algebraic variety, you have some expected dimension of the intersection. So you can compute the expectation for the dimension, but sometimes you have the phenomenon of dimension excess. So the intersection might have the dimension larger than the expectation. So this is basically a part of Fulton intersection theory. And here we have to do the same for currents. And this also a generalization of some famous Lalong number theory. So in the Lalong number theory, the second current is just a point. The second current is just a point, and then you have Lalong number theory. But here we develop a more general theory. But this is not enough for us. We have to develop this again with Nguyen in the case where the current is not closed. The current are not closed, only ddc-closed, only harmonic. And then the situation is more complicated, but we can do that. And then it's the main technique that we use in the proof. So let me finish by giving you the very rough idea of the proof. So I come back to the theorem of unique ergodicity. So assume that there is no invariant closed current. And then I want to show that there is a unique harmonic currents. So I assume that there are two. So T and S of mass 1, there are two currents. And I fix a Kaehler metric on the surface. So because T and S have the same mass, basically it's equivalent to say that you have one equation. This equation coming from the mass. So the mass of T is equal to the mass of S. And then this is the equation of this. Okay, so we have t minus s with omega. The integrand is equal to 0. So now, using the theory of density of intersection that I told you before, we can show that the intersection of t with t is equal to 0. The intersection of t with s is equal to 0. The intersection of s with s is also equal to 0. So now we have some Riemann type theorem for compact Kaehler surface. And so we have some signature theorem. Riemann is a signature of some bilinear form. And because we know the signature, so you have some Cauchy-Schwarz inequality. And then using this Cauchy-Schwarz inequality, you can show that actually this difference, T minus S is closed, the closed current. But it's not necessarily positive. It's not necessarily positive, but you can decompose this because you know that the current is directed by the foliation. Then you can decompose this into positive part and negative part, like a measure. And then each of them are closed. And then there's a contradiction because we assume that there is no positive closed current. We assume that there is no positive closed current. So here you get the contradiction. So, however, we have a very, very difficult technical problem here. So to compute this, if you have no singularities, then it's easy. I mean, relatively easy. But because of singularity, so we have to do some computation. And it's very technical, and it's very, we use some local information and some estimates. And recently, with my student, we showed that the estimate that we use is optimal. So you cannot have any better estimate and then it's very, I mean, very technical, and fortunately we end up with this computation and give us that the intersection equal to 0, and then this is a proof of the theorem. Okay, so let me stop here. My time is over. Yeah. Thank you.
Thank you very much. Any questions, comments?
Does your classification theorem have anything to do with the cone theorem in like Mori theory for these algebraic surfaces?
Which theorem you are talking about? Cone theorem?
You had a theorem where you described precisely where you classified all the different types for the for F with hyperbolic singularities.
Yeah.
I mean, given the statements about Neff and big, it sounds like that it almost has to do with something with the with like the Mori cone theory.
Oh, maybe, but we didn't go further. Here we have something more or less come directly from the proof that I talk about. But then probably in the situation of the second scenario here, probably we can go further and have some kind of more precise classification of surface. I don't know about this. What I know that there are many examples, and some people studying this, and I guess that is maybe more complicated than it looks like to classify all this surface with such a situation.
Okay. Thank you.
Yeah, it's go by on my capacity of this. Yeah.
So I wanted to ask you, you mentioned something about that it generalizes the algebraic theory of intersection of varieties. I vaguely remember there's this non-trivial thing that compares show groups, like groups of cycles, and maybe homology. So do you have something that generalizes it?
So the situation is different because in the Fulton theory they have varieties. So at least the support of these varieties are clear as some algebraic set and so on. You can consider object on this set. But in our case, T and S are currents. So the support of current is, in general, is very complicated. And it could be everything, but the current could be singular, but like a measure. So you take a measure, the support doesn't tell you many information about measure, yeah? So the problem are different. So what you can do here, so given two currents, we can always decide it, what is the dimension of the intersection, for example. Okay, because we have generically you have some expectation for dimension, but it could be larger. Okay, so you can decide, we can compute the dimension of intersection, and you can compute the cohomology class of the intersection. Even the direction, even the intersection doesn't exist in the sense of currents, but you can compute the cohomology class of this, and then you have some information like that. One of the application is the following. You consider that we use actually. You consider, for example, classical dynamical systems. So you want to consider the distribution of periodic point. Okay. So periodic point are intersection of the graph of Fn, of the iterate of F with the diagonal. Okay. But the intersection might have, you expect that the dimension of the intersection is 0, but actually it could be larger. It could be larger than 0. So, but you don't care about, I mean, you want to counter, for example, only isolated singularities, for example. You don't care about the accidental fixed points or periodic points or varieties and so on. For example, like that. Okay, so you can try to take the limit when the iterates, so when time go to infinity, and for example, you can show that you can have dimension excess, but the dimension excess becomes smaller and smaller when go to infinity. For example, some information like that, some kind of application. But we are not going to the direction of cohomology in the Fulton theory because this may be not really meaningful in our case, at least for some theorem. Yeah. So this is what we can do. Yeah.
Okay, so thank you very much. That was very enlightening. Any more comments? We're a bit out of time, so maybe some of the people can write to Professor Dinh. So thank you very much for attending our colloquium, and hope to be in touch.
Yeah, thank you very much for listening.
And then thank you for staying at work for so late.
Yeah, it's okay. Okay.
Okay.
So, see you. Thank you very much. Thank you.
Stop the record.